In this video, we will continue our investigation into power series representations by starting with the function arctangent of x. Recall, the main idea behind our approach is to somehow relate back to our common formula, 1 over 1 minus something. We can relate back to this formula via algebraic manipulation, but also using calculus in terms of differentiating and integrating. And in this case, we might want to recall the following, that the derivative of arctangent is equal to 1 over 1 plus x squared. With that in mind, we can rewrite arctangent as being the definite integral from 0 to x of the function 1 over 1 plus x squared. Now that we've written it as 1 over 1 plus x squared, we can observe that if we find a power series representation of this integrand function, then we could integrate that power series using a previous formula. So let's do a little bit of work to the side. 1 over 1 plus x squared is equivalent to 1 over 1 minus a minus x squared. And that minus x squared is the something which we will plug into the formula above. So this becomes the sum from n equals 0 to infinity of that something minus x squared raised to the nth power. And this will converge as long as the absolute value of minus x squared is less than 1, which is equivalent to the absolute value of x being less than 1. Simplifying just a touch, the minus gets hit to the n and the x squared gets raised to the n. So this can be written as the sum from n equals 0 to infinity of minus 1 to the n x to the 2n. And now we can take this and plug it inside the integral for 1 over 1 plus x squared. That is, this is the integral from 0 to x of the power series, the sum from n equals 0 to infinity of minus 1 to the n. And instead of an x, we're going to use the variable t, so t to the 2n dt. And up above here, to be technically correct, we should come back and note that each of the x's should be replaced with a t. And now we can think of taking the integral and plugging it inside the power series. That is, we can write this as the sum from n equals 0 to infinity. Minus 1 to the n is a constant with respect to t, so pull that out. The integral from 0 to x of t to the 2n dt. Well, when we anti-differentiate t to the 2n, that would give us 1 over 2n plus 1 t to the 2n plus 1. You plug in x, minus sign plug in 0, but when you plug in 0, you're always going to get back 0 for t to a power. So this is x to the 2n plus 1, and this is all over 2n plus 1. And because the radius of convergence of the power series we are integrating is 1, integrating does not change that. So for the power series representation that we've come up with for arctangent of x, there's also a radius of convergence 1. Note that this is a very common approach. The key idea is to somehow use algebraic manipulation or calculus to relate back to this common formula. In the given example, the observation was the derivative of arctan is 1 over 1 plus x squared. We have a power series representation for 1 over 1 plus x squared, so we simply anti-differentiate to come up with the desired power series for arctangent. And at this point, I would like to begin generating a list of common power series that should eventually be committed to memory. And at this point, it's going to contain two functions. the first of which we just generated. Arctangent of x is the given power series and has a radius of convergence 1. And additionally, let me note there's a small typo here. Both of these sums should start off with a lower index of 0. Something we'll see a bit more in future videos is that the power series representation for e to the x is the sum from n equals 0 to infinity of x to the n over n factorial. And both of these power series can be represented a bit more generally. Instead of using the variable x, we can replace that, as we've done before, with a blank. So arctangent of something is the sum from n equals 0 to infinity minus 1 to the n over 2n plus 1 multiplied by that something raised to the 2n plus 1. For example, if you wanted a power series representation of arctangent of x squared, you would simply plug x squared into both blanks and then simplify. In terms of the radius of convergence, it will be whenever the absolute value of that something is less than 1. And you can manipulate this inequality to determine that radius of convergence. Similarly, e to the something would be the sum from n equals 0 to infinity of that something raised to the nth power divided by n factorial. And let's see how we can use these to write down one of these more general power series. So let's determine a power series representation for the function e raised to the power 2x squared. So as we mentioned moments ago, the power series representation of e to the something will be the sum from n equals 0 to infinity of that something to the n over n factorial, and the radius of convergence is infinity. So in this case, the something that we are using is 2x squared. So the power series representation will be the sum from n equals 0 to infinity, well, of that something, 2x squared, raised to the nth power, all divided by n factorial. And then algebraically, we should get this down in terms of a typical form of a power series. That is, we need to do this algebraic manipulation, take the nth power and hit the x squared, and hit the 2 with it. That would be the sum from n equals 0 to infinity, 2 to the n over n factorial, x to the 2n. And the radius of convergence will be unchanged, still infinity. So as long as we have those two common power series committed to memory, we can easily find power series representations related to arctangents and exponentials when you compose them with a simple function.